Thanks for the introduction, and also thank you very much for organizing this very successful talk series. And I think we've had, I've enjoyed the talks we had greatly. I think there was some great talks, and it's a great way to see lots of recent cutting-edge research. I have to say that this talk is going to be a bit different. I will not stand up to maybe the high standards set by a lot of great speakers recently, and this is not going to be so much a talk about a recent paper. I'll mention several papers, including one actually fairly recent paper, but more the aim of this talk is to try to think about how heterogeneity and the idea of pluralism fit in distributed and federated learning. And along the way, I will discuss some recent papers, some work with a variety of co-authors, recent work with Blake and Kshitij, two students at TTIC, and some other work with past collaborators at TTIC University of Chicago, and also a group at Google. Okay, so let me just start by, I think that I'm not going to motivate federated learning, because I think all of you know why you're here. But just to make sure we're on the same page, let's start by just thinking of what the federated learning process or optimization mechanics look like. And okay, this is not working. Just a second. Okay, it's working now. Okay, and the basic framework in federated learning is we have a big pool of devices that we'll take here mostly to be maybe infinite even. And at each round, we select some random subsets of devices from that pool and communicate with those devices. The devices perform some computation based on some local data on that device and communicate back to the server or the cloud. In the next round, again, we choose some other subset of devices, communicate with them. Each device computes based on several examples. And here, the rectangles, the darker rectangles, if you can see the pointer. Let me see if I can make it so you can see the pointer. Okay, excellent. Each one of these squares, you can think of it as one a data point or one stochastic gradient estimate in each one of the devices. Okay? And the process repeats for several stages. Now, the thinking about this process is fairly different from what I think of traditional distributed optimization in the data center or in a cluster, but the actual computational structure is actually fairly similar. So let's if we compare this to computation on a cluster of machines and a bunch of servers, we usually have several servers, and they perform stochastic gradient computations locally, and then every so often they aggregate and communicate between them. Okay? So these models, they do have lots of these two settings of federated learning versus computation, distributed optimization learning on the cluster, do have some differences. So the one is that in federated learning we have typically different devices at each iteration, whereas here we're thinking of each machine. Each machine is like one big server that persists across computation steps, and this also leads to maybe a difference that'll come back later, where what's flexible and what's fixed is different in these models. So in a traditional distributed optimization on a cluster of computers, the number of machines, number of servers is fixed. I mean, I have a data center with a certain number of machines to my disposal, and I want to compute in those, like 100 or 1,000 or 10,000 machines. And oops, I see there's a, okay, and what I can change though is how frequently I communicate. And so these machines can communicate more or less frequently. In a federated learning setting, the game is a bit different, because they really have an infinite number of devices they can connect to, and what I can choose when running this is how many devices am I going to use at each iteration. Where I'd rather use fewer devices, but this is really something I can control. What I cannot control is how frequently I communicate, because it's not really how frequently I communicate, it's just how much data is on the device. I mean, you're typically exhausting all the data on the device in each one of those steps. Okay? So that introduces some differences. The scales are also sometimes different. Federated learning, we typically maybe have more devices available, but the number of rounds is maybe relatively small because there's lots of overhead in communicating. And something we'll get back to later is heterogeneity, whereas when we're doing distributed optimization server, on the server farm, we can typically take all our data, shuffle it, and even if it wasn't homogeneous to start with, pretend it's homogeneous. And as we'll be coming back to later, when we're talking of federated learning, we have to deal with lots of issues of heterogeneity. But for now, let's set aside actually these differences and focus on the similarities and see that in both of these models, in federated learning and in distributed optimization in the cloud, the basic computation structure is the same. In both of them, what we have is we have a sequence of rounds. We denote that as R rounds. At each round, we have M machines. On each machine, we do K computation steps, which I'm taking here as K stochastic gradient computations. And then we can, within those K steps, we can only communicate within each machine. And then after each round, there is a communication round involving all the information from all the machines. Okay, so this is the case both in the distributed optimization on a server farm and in federated learning. So the actual communication structure is the same, and this is this structure of M machines with intermittent communications between them. And this is this structure, it's useful to formalize this. We did so in this paper on the graph oracle models for distributed optimization, where we formalize different distributed optimization setting using the communication through the communication graph that define them. And here, both of these are defined by this intermittent communication graph. Now, so when studying these from optimization perspective, really they're the same model to study, and we can ask how well can we optimize in the setting where we have stochastic gradient accesses, but these stochastic gradient accesses each one a sequence of local stochastic gradient accesses with communication between them only intermittently. Now, I want to point out that the analysis of what's the best error I can get with a fixed structure is the same in both of them. What's maybe a bit different is how we interpret that. So let's take, for example, what I would consider as the simplest baseline here, which is mini-batch stochastic gradient descent. So in mini-batch stochastic gradient descent, what we do is the way we use this communication structure is let's go back here. The way we use this communication structure is by computing on each machine the K stochastic gradients at the same point. In fact, all machines compute stochastic gradients at the same point. And overall here, when we communicate, we have a total of K times M stochastic gradient estimates all computed at the same point, which we can use as a mini batch to obtain a much more accurate stochastic gradient estimate at that point, and then take a stochastic gradient step based on this estimate. So we're using mini batch. We can implement in this framework mini batch stochastic gradient descent with a total of K times M mini batch size and R steps of stochastic gradient descent. Okay, so and we know how well that performs. That's the classic analysis of stochastic gradient descent with M machines, K stochastic gradients per round per machine, and R rounds. We know we can get an error that scales roughly as square root of sigma squared over RKM, plus 1 over r. This is for a smooth, convex, not necessarily strongly convex objective. Now, what this tells us now is maybe a bit different in those machines. So this is the error that we get once we fix number of rounds, the number of steps per round, and number of machines. But as you recall, what we actually fix and what we vary might be different. So in particular, in this root optimization setting, what we might be asking is, well, I have a fixed number of machines. My server farm has 1,000 machines, and I'm going to run it for some fixed amount of time. So k times r here might be fixed. And what I can vary is the communication frequency k. And the question we frequently ask is, how infrequently can I communicate? How much can I reduce my communication? But knowing the optimization suboptimality is a function of k, r, and n, immediately allows us to get that. What we have to ask is, fixing k times r, how large can we make k without actually this error bound suffering? So without losing statistical efficiency when the first term here remains dominant, and this additional term that's introduced by the infrequent communications does not become the dominant term. And we can simply work it out, and the answer is that we need to communicate roughly every square root of t over m rounds. Now, for the federated learning setting, based on the same optimization analysis, we might ask a different question, which is, for example, how many devices do I need at each round? Right? So I already know that I'm going to be running for 3 days or 4 days or however number of days. So the number, if I can make a round every 15 minutes, that sets the number of rounds that I have. And what I want to ask is, how many machines should I use each round? The number of data per machine, so k is also fixed. And how large do I need to make m? And the answer here now is I want to make m large enough. This is the term that I can control. So I want to make m large enough so that this term does not become the dominant term. And I am bound by this term of 1 over r, and 1 over number of rounds, which is a term that in the federated learning case, I cannot actually play with this fixed. Okay? And in this case, we can also, based on the same analysis, we can also now answer this question. And we can calculate that the number of machines you need per round scales as roughly r over k. Okay? So note, the main point I want to make here is that even though the questions we might ask and what might be fixed and what might be different between those two setups, in terms of the actual study of what is the suboptimality is the same study in both of them. It's the same communication and computation model. And answering this basic question of what is the best suboptimality we can get with a fixed number of machines m, number of rounds r, and number of steps k per round, once we know the answer to that, we can then easily answer all kinds of questions we might want to ask, like, how much can we reduce communication, how many machines we need, and so forth. So this is really, I think, the basic question to ask you. Just what's the suboptimality we can get in this case? And I think you maybe heard talk by Blake a few weeks ago, I think it was a couple of months at this point, where we looked exactly at this question, at what can we do in this communication model. I should say that, so we already saw that one kind of baseline is mini-batch stochastic gradient descent, and which gives us this suboptimality. And one thing, of course, we can do is we know that mini-batch stochastic gradient descent is not optimal, and we can always accelerate it. And following the analysis of by George Lan, this reduces the optimization term from a dependence on 1 over the number of rounds to 1 of the square of the number of rounds. Okay, and now we can ask, is this optimal? So I want to point out here, this is, I think, maybe the most fundamental question here. In a sequential optimization model, if we just have a single machine performing t stochastic gradient excesses, we know exactly what the optimal method is. And this is actually answered by this paper of Lan. It's just the accelerated stochastic gradient descent. And so we know what the method is, and we know what is the min-max suboptimality, what is the best we can hope for. And now we can ask the same question also in this distributed model where we have n machines. What is the min-max complexity here, the min-max suboptimality? What is the method that achieves it? So we can ask, maybe a first guess is to ask whether we can even improve over accelerated mini-batch stochastic gradient descent. And the answer, we can immediately see that mini-batch stochastic gradient descent is not optimal here, because we have another method, a much simpler method that's actually better in some cases. And this is the following very simple method of ignoring all but one machine, just using a single machine and performing a single stochastic gradient descent chain in a single machine. Okay. This is a very simple method. It doesn't depend at all on the number of machines. Right. And has complexity, it has the suboptimality, which is just the suboptimality of stochastic. I'm missing something. Okay, I'm missing something here. This should be okay. Let me skip this for now, because I'm seeing I'm confused myself also. Yeah. So okay. I'm missing here the sigma squared, but also what I want to say that in some cases this actually might be better than okay. So right. So I'm missing here. Let me try to. Okay. So missing here a sigma squared in the numerator. And the thing is that the surprising thing is in some cases a single machine might be better. So if k is very, very large and r is very small, then the 1 over r squared term might actually be larger than square root of 1 over r sigma squared over rk, in which case a single machine SGD might be better than mini-batch SGD. And so we see that, I mean, mini-batch SGD is definitely not optimal, because in some cases even this very, very, very simple alternative baseline beats it. And I think for a very large time, these were kind of the two trivial baselines, accelerated mini-batch SGD and single machine SGD. And we didn't have really any method that improved over both of them. And it clearly, I think to me, clearly there should be something that at least is good as both of them, and hopefully also improves. So as Blake described several weeks ago, we now do know that it is possible to improve in some regime over both of them. And this is using the very popular now local SGD method, or federated, known as local SGD or federated SGD. We used to call it parallel SGD. And I'm not going to go into the details of the method because I think it's been covered by several talks here recently. The basic idea is that we perform SGD chains separately in each of these machines, and then average the iterates every communication round, and then again perform separate SGD chains. And the analysis that Blake presented several weeks ago was the first analysis. So this method seems like a very obvious method here, and is in fact used quite a bit, but its analysis remains kind of tricky. And Blake showed a few weeks ago here the first analysis that does show that local SGD improves at least in some regimes over both accelerated mini-batch SGD and single machine SGD. And the analysis that Blake presented has this unavoidable statistical term. Another term here, 1 over rk, which seems sensible. I mean, corresponds to just the fact that we're optimizing over effectively 1 over effectively r times k sequential steps. But then it has this additional term here, which sometimes could still be worse than just GV, but in some regimes, when the number of machines is not too large and the number of rounds is reasonable, can be lower than the mini-batch SGD error, and show improvement. And we can still now ask, okay, is this the best we can do? And we don't know. So we can also show a lower bound here. And as you can see, there's still a very big gap between local SGD and the lower bound. So the lower bound is an algorithm-dependent lower bound. This is kind of a lower bound on the min-max rate. And the main reason I put this slide up here, even though this all was covered in Blake's talk, is really to emphasize that I still think that this is, before going even to heterogeneity and all kinds of fancy things with federated learning, this is a super basic thing about distributed optimization that we still do not understand. In this very simple model of distributed optimization with intermittent communications, what is the min-max rate? What is the best we can achieve, and what method achieves it? We still have a huge gap between these upper bounds. Each one of them is good in a different regime, and the best we might hope for. And I want to advertise recent work by Honglin Yuan and Tengyu Ma. I'm not sure if either of them are here in this talk now. Honglin and Tengyu did give an improvement over local SGD by accelerating it. So taking Minibatch HDD, we know we can accelerate it using Nestor of acceleration and reduce the optimization term by squaring the optimization term. Local HDD does not involve any acceleration. It's rather tricky to accelerate at local HDD. It's not as easy as just throwing in the exact same Nestor of updates. Honglin and Tengyu managed doing that and got a variation of local HDD that includes acceleration. And in the same way that here we get another factor of R in the denominator, also in their analysis for accelerated local HDD, both of the optimization related terms get an extra factor of R in the numerator. Now, this is very interesting, and it's a substantial improvement over local HDD. There's still a big gap here from the lower bound. So in particular, I want to point out, one is that the acceleration here is only by a factor of R and not by a factor of RK, right? So if you compare the upper bound here, this is the upper bound without acceleration, it behaves as 1 over RK. The lower bound is a lower bound that corresponds to sort of what you might expect to get an acceleration, which has this term squared, 1 over R squared K squared. And what Tengyu and Honglin managed to get is an acceleration which squares the R term, the number of rounds. So in some sense, you get a benefit of acceleration for each round, but there is no acceleration within a round. So the K term is not squared. So this is one looseness here versus the lower bound. The second thing is that we still have this additional term here, this sigma to the 2/3 term, and we do accelerate it, but we do not know if this term is necessary at all. So it's not, I'm not aware of any lower bound that indicates that we must have, we know that this term, if it's a similar term at least, is necessary for local HDD, but in an algorithmic independent manner, we do not know if this term is necessary, or if there's some method that avoids in this term altogether. So there's lots of gaps here, and still lots of interesting questions to understand for understanding distributed optimization. And again, I think these are super basic questions. It's a bit maybe embarrassing that we've been looking at these settings of distributed optimization with intermittent communication, this exact model for maybe close to a decade now, and we still do not know the optimal method. We do not know what the min-max rate is. Okay, any questions so far? Great. Okay, so far I did not mention actually heterogeneity. I mean, this analysis refers to a fully homogeneous setup where we have all of these stochastic gradient estimates each one of these squares, a stochastic gradient estimate from the same objective. Another way to think about it is all the machines have the same same data distribution or same objective and are sampling from the same data distribution, computing stochastic gradients of the same objective. But as we mentioned before, the maybe bigger and more interesting challenge with the distributed optimization, sorry, with federated learning is heterogeneity. And unlike in the data server setting where it's maybe easier to achieve, to kind of homogenize the data by randomly shuffling, in federated learning, we typically can expect different machines to really have very different data distributions or different objectives. And one can ask in this case, I mean, there's all this analysis that we saw here for local SGD, for example, in mini batch SGD, how much of this carries over also in a heterogeneous setting? I mean, for example, the conclusion here that we saw that local SGD is sometimes better and sometimes worse in mini batch SGD. Does this also carry over to heterogeneous setting, or is it heterogeneous setting? Does mini batch SGD break down? Does local SGD break down? What can we say in that case? And fairly recently, we extended our analysis also to this case. This is, I should say, work with Blake and Kshitij, two students at TTIC. And what we analyzed here, and this is the same setup that several papers presented here also looked at, is a setting where each of the M machines has a separate local distribution, so local objective, Fj, and calculates stochastic gradients of its local objective. And our goal is to minimize the average of these local objectives. And this seems like a more challenging setting, and we can ask, well, in this case, is it still very difficult to beat mini batch SGD, or is it that in this setting, mini batch SGD, which is a very simple method, kind of breaks down, and we do in fact need to go to more complicated methods? In analyzing this also, a parameter that others and we have also used is, if we want to talk about how related are these machines, so are these distributions. If all of these local machines have very, very, very different objectives, then the situation seems like it might be much, much more difficult. And so we introduce this, we look at this parameter zeta, which roughly captures the variance between the machines. So not what's the variance of the stochastic estimates on each machine, that's denoted by sigma, but rather different are the how different are these objectives Fj from their average. Okay, so what can we say in this case? So it turns out that accelerated mini batch SGD is actually completely unaffected by this heterogeneity. Yeah, despite the heterogeneity, we get the exact same guarantee for accelerated mini batch SGD. Okay? And so in some sense, in the heterogeneous setting, the things tip over even more to the favor of mini batch methods. In actually local SGD, it becomes even harder for local SGD to improve over mini batch SGD. And we have actually an advantage for the simpler methods. We were able to obtain a guarantee for local SGD also in this setting. So the first three terms are the same terms that we had before in the homogeneous setting. And what we see here is that we have an additional term here, which involves zeta squared, this parameter that measures how heterogeneous is the problem, over r to the 2/3. Now, at least if zeta is very, very small, then this term is small, and you can think of this as this third term is sort of smoothly interpolating from the homogeneous setting to a setting in which is, I would say, almost homogeneous, where zeta is very, very small. But very quickly, once the machines start becoming really different from one another, this third term here becomes significant, and local SGD stops being better than accelerated, than even unaccelerated, than just mini batch SGD. So it seems that actually in this heterogeneous setting, local SGD is very problematic and might be much harder to show improvement for local SGD over mini batch SGD. I should say also that Hongline and Tengiu's analysis is not, at least as is valid here. If somebody wants some nice project thinking of how to accelerate local HDD in the heterogeneous setting is still open as far as I'm aware. But really more significant, I want to focus on this third term here. So in general, if the machines are very different from one another, we'd expect zeta to be of order 1. This is kind of the unrelated case. And if zeta is of order 1, this term here, 1 over r to the 2/3, becomes the dominant term and makes local HDD in this case very, very bad. In fact, what we can show is that we can that a term like this is in some sense unavoidable. So we can establish a algorithm-independent lower bound here and show that any method in this setting must have a dependence on zeta squared over r squared. So what this tells us is that if we compare this to the accelerated mini-batch S3D rate, we see that when this heterogeneity is high, meaning the machines are effectively unrelated, we don't require them to be very, very similar to each other, then accelerated mini-batch S3D is already optimal. Okay, so we cannot improve over accelerated mini-batch S3D at all. Okay, so this, to me, was, in retrospect, everything is makes sense, but when we first noticed it, it was a bit surprising. Again, what this means is that actually, we saw that in the homogeneous setting, local HDD can improve over mini-batch methods in some regimes, whereas what we can see here is that in the truly heterogeneous setting, when the heterogeneity is high, then actually local HDD can never improve over mini-batch HDD. And in this case, we actually do know exactly what the min-max rate is and what the optimal method is, and the optimal method is just the baseline accelerated mini-batch HDD method.
So I would have a question, if I may.
Sure.
Can I?
Sure. Yeah.
So there is even a more truly heterogeneous data setting, and that's the one where this constant is infinite. Do you have any comments on that?
So, well, I'm not sure how. At least in our setting, it would not be infinite since we're requiring the problems are Lipschitz. Then zeta squared is always bounded by the Lipschitz constant.
So there's another underlying assumption somewhere here.
Yeah, so we are assuming here this assumption is not necessary for the analysis. So the analysis, okay, so the only thing assumed, okay, so actually let's break that. For this analysis, the only thing we're assuming is that the objectives are smooth, and we're not assuming that they're Lipschitz. We're assuming that they're smooth, and we're assuming that the variance of the stochastic gradient state machine is sigma, and this assumption about the heterogeneity, in which case you're right that zeta could be infinite. The way at least I think about this is I think about this usually when I think of zeta as bounded kind of by order 1, since I think of the objective as also being Lipschitz. I mean, this is not, when this is not an assumption used to get these bounds. This is more like how I think of the setting. Okay? Does that clarify? I know that doesn't answer your question, but does it clarify in terms of the assumptions?
Yeah, I understand
okay,
that. So,
okay,
so
sure.
normally when I think of heterogeneous data setting, I like to set this to infinity and not have any kind of data similarity.
Sure. Right. So
assumption.
I agree. So in this case, when things are just, I agree. In this case, is what I would consider as a completely heterogeneous. Then the mini-batch
some kind of interpolation, between the two. Yeah. Okay. Thank you.
Mini-batch SGD. So in that case, mini-batch SGD is not affected. So you could set zeta to be as high as you want, or unbounded, or infinite. And accelerated mini-batch SGD is still optimal. What happens in this case is local SGD might completely fail. Okay. So in local SGD, we do have a lower bound that depends on this variance parameter. And so if you do not assume anything about it, then if in the truly heterogeneous setting, two things happen. One is accelerated mini-batch SGD is still valid and is still optimal. And the second thing is that local SGD can fail horribly in the generic heterogeneous setting. Peter, does that answer your question? Or?
Yes, thank you.
Okay, excellent, thanks. Okay. Right, so somebody asked if setting zeta to 0 recovers the homogeneous setting. So the zeta, as I defined it here, setting it to 0 does recover the homogeneous setting, because we set zeta to 0, then that means that all the local gradients are the same, all the local objectives are the same as the global objective. Strictly speaking, up to maybe an additive shift that doesn't change anything. So this does recover the homogeneous setting, and in fact, in this case, this third term goes away, and we do get back exactly the homogeneous setting. So these guarantees exactly recover the homogeneous setting when z equals to 0 and interpolate from them smoothly when zeta becomes large. So this is an answer to a question in the chat. Does that answer your question? Okay. Okay. Let's see. Okay. Great. Okay, I should also note that there's some subtlety with exactly how zeta is defined, the way defined zeta here. So I encourage you to look at this paper. The paper is an archive for more details. There are some subtleties. The way defined zeta here is a bound on the variance of the local objectives at every point. You can also define zeta as the bound on the variance of objectives only at the optimum. And then in that case, setting that parameter to 0 does not exactly recover the homogeneous setting. And again, I encourage you to look at the paper for different ways of defining the heterogeneity. Okay. Right. Okay, but let's. So this is heterogeneity, but really, what I wanted to mostly talk about. Well, I see I'm actually starting to run low on time. What I mostly want to talk about in this talk is idea of pluralism. So the thing is that I would argue that this analysis, in any case, is maybe not the right analysis, not the right question to look at anyway, because if different devices have different data distributions or different objectives, then why do we want to actually why should we look for a single model that's good for all of them? So if a better approach in this case would be to learn a separate model for each device, because the devices, if I use American English in my device and somebody else uses British English or maybe a completely different language altogether, and because of that there are differences between these devices, why should I insist on using the same model when the objectives are different? And so a pluralistic approach in this case would be to learn a separate model for each device. So you can also think about this as incorporating personalization into the learning. And the main kind of thing I want to emphasize here is this is good not only for personalization, but also can assist in optimization, because it relieves this tension of trying to seek a consensus, which is often the difficult part in the optimization process. Okay? So now, at extreme, we could do this independently in each device with no communication at all. But I mean, that kind of defies the point, because then we'll need lots of data on each device. We're not leveraging at all the fact that we also, the data that on other devices, and the fact that even though these objectives are not identical, we still expect them to be similar in some sense. And maybe the more correct way to approach this is a multitask problem, where we have a task on each device, and the tasks are somewhat related, even if they're not identical. And now, to make progress here, we have to talk about how related are these tasks. I'm not going to go to any of these details here, but we can talk about different models of relatedness. For example, different devices use the same features but in different ways, or just are small in Euclidean distance, and get an analysis for this distributed multitask setting where things again are distributed. We have different data distributions on each machine, and what we want to do is leverage the similarities and communication to find good solutions, but without insisting on consensus. But really, the type of heterogeneity we talked about so far is a very simple kind of heterogeneity, where the data, where what's varying is just that every machine has a different data distribution, and in that case, really we should maybe look at the problem as a multitask problem. But in federated learning settings, we also have lots of other types of heterogeneity. For example, different devices might have different amounts of data. Some of them might be faster than others, so we might have different delays. Again, this sort of disturbs this standard model. And all this becomes much more complicated, because all these differences are also correlated with the distribution on the machines. So for example, if you have a situation where users, so generally, if all the machines had the same distribution, some of them were faster and some were slower, we could just say, oh, we'll just use the faster machines and not worry too much about the slower machines. But the problem is that if the slower machines, the devices that maybe are take more to communicate, tend to have a different data distribution, that users of a specific type are maybe older machines or slower machines with not as good network connection, then what that would be doing effectively is starving out a whole set of machines. So really, I think what makes all this challenging is that we have correlations between the data distributions in different machines and other parameters that are varying between them. And what I want to try to argue here is that, again, the idea of pluralism, of using, instead of insisting on a consensus on one solution to each machine, allowing us to have different solutions for different machines, might alleviate, also help us deal with the situation of having other things varying between the machines. And what I'm going to do for the remainder of the talk is demonstrate this, at least with one type of heterogeneity, and this is the fact that we have differing availability of machines throughout the day. So different machines are available in different parts of the day. And this is joint work with the group at Google. Some of these people are still at Google, some not. This is with Hubert, Tomer, Brendan, and Kunal. And so the starting point with this work is that so now let's for a second ignore even the distributed setting and just think of standard SGD. So we know that SGD is great. If we just do SGD, I mean, again, as we mentioned before, it's in a sequential setting, it's an optimal method, and it really is great. But as probably many of you discovered in your maybe first time you used SGD on a real data set, SGD is great if you run it on randomly shuffled data, on IRD data. Okay, if you take your data and your data is, for example, sorted, sorted in this case alphabetically, or maybe all the positive examples are in the first half of the file, and all the negative examples in the second half of the file, and you try running SGD on that, that's going to fail miserably. So this the random shuffling is very important for SGD, and as we just mentioned. In federated learning, things are frequently not exactly random shuffled. So, for example, one variation we have is the urinal variation throughout the day. If you have, typically in federated learning, devices participate when they're kind of plugged in and fully charged and on a Wi-Fi network, which is typically maybe at night. And since night is different in different parts of the world, this causes the urinal variation where during nighttime in the US, you have lots of American English devices available, and then when it's night in Europe and then the UK, you have British English devices available, and then later on, when it's night in India, those devices become available. And so we really have these strong diurnal variations. So what we're doing here when we're doing it, whether it's mini batch SGD or local SGD, we're doing SGD on data that's not randomly shuffled, that has cyclic variations. So the first thing we can ask is, how bad are these cyclic variations? Because we're not really talking about things here being completely sorted. I mean, it's only maybe 3, 4, 5 of these different kind of blocks that appear and disappear. So the setting to formalize this, the way we'll think about this is that optimization is separated into blocks. We have B blocks here. So you can think of B as, maybe in this example is 2, just purple and green. So in this case, B is equal to 2, or B might be equal to US, UK, and India, so 3, or you can maybe have a block for each day, so maybe, sorry, a block for each hour, so 24 blocks, okay? We have a blocks B, and for each block, there's a distribution, each block I, there's a distribution DI affiliate associated with that block. What we want is just to optimize with respect to the average distribution, but in each block, we see just samples sampled from that block. So we see a bunch of purple samples, then a bunch of green samples, and again, purple samples, green samples, and so forth. So if we have a small number of blocks, even just 2 blocks, can this be really bad? I mean, how bad can this? So the first thing I want to point out is that it's easy to show that this can be really, really bad. So training on such a block cyclic data, even with just 2 blocks, can construct example in which is arbitrarily worse than random IID data. Okay? In the situations this is worse is situations in which both of these blocks are very kind of different and competing. So one of the data distributions need to use a feature in one way, the other block needs to, the other data distribution, the other block needs to use it in a different way. And to reach consensus, they really need to kind of negotiate between them. And so the number of cycles of negotiation becomes important. And if things are randomly or IID sampled, then you get lots, these are interleaved, and you get lots of, roughly speaking, these negotiations. But when things are in blocks, then this process can be much, much, much slower. Okay? So note that in this case, what we said is that the problem arises, the slowness here is because we need to kind of reach a compromise between the purple and the green to find something that's good both for the purple and the green, and that takes a lot of going back and forth between them. But a pluralistic approach here would say, okay, I mean, if the purple and the green are really so different, then why not just learn a different model for each block? Okay, so this would be a pluralistic approach here, where instead of training a single model, W, we train a purple model W1 and a green model W2, train the purple model just on the purple data, and the green model just on the green data. So this is a great pluralistic approach and completely alleviates this problem. The only problem is now for each one of these models, we have B times less data. So if B is equal to 2, maybe it's not so bad. But if you think of B as equal to 24, maybe, that means we have 24 times less data. So if we have a different block for each hour. Or in other words, training would take 24 times longer. So instead of training taking 2 days, training will now take 2 months. Okay, so this is a not acceptable solution because we're kind of not, we have this pluralism, but we're not leveraging the similarities. Okay, so what can we do here? Now that we have a contrast here where the failure in the first case of doing just a single SVD chain was because things were very different between the machines, okay, when you really need a lot of negotiation. But in the second case, when things are very different, then we're actually fine. I mean, what we're losing here is when things are similar between the machines. And so it's similar between the blocks, and we're not leveraging the similarity. So can we think of something that would work always, that would, if things are similar, would leverage the similarity, if things are different, would not worry about it and allow things to be different? And moreover, do we need to explicitly encode what type of similarity we have here? Like in the multitask case, where it was important to encode what type of similarity we have between machines. So it turns out that in this case, we can have an optimal solution that kind of gets the best of both worlds. It works on this block cyclic data, and it doesn't have to even understand what type of similarity or not similarity appears here. And this solution is the following very simple solution. We train the models separately. So we do train just like in the standard we train the model using a single SVD chain. Okay? So just like in the ignoring the fact that we have differences, we run a single SVD chain. Okay? So we train on the purple models and then switch to training on the green models, but just in the same model. So we run a single SVD chain. But what we output is, instead of outputting a single model for all the machines, we recall that when you run SVD, what we output at the end, at least based on the theory, we have to output an average over the iterates. So what we do here is, when we're done running the SVD chain, the model we output for use in each of the blocks is just the average iterate within those blocks. So again, so we run a single SVD chain, and then at the end, we take the last purple block, average the iterates on that purple block, and use this for the purple data, average the iterates in the last green block, and use that in the green data, okay, for the green example. So again, if purple here, think of purple as the US and green is Britain, we run a single SVD chain, but then use, for the users active in American kind of times, use this average of iterates, and for the British ones, use this average of iterates. Okay? And what we can show that this is we get exactly the same guarantee that we would have gotten had we used random shuffling. So we get absolutely no additional cost here for the fact that the data is not IID shuffled, with pretty much no extra computational cost or overhead. The only difference here is that how the averaging is done at the end. And this is possible only because of the fact that we allow this pluralism. If we insisted on outputting a single model, we can prove that no matter what you do, you would have this horrible slowdown.
So now I have a question. Yes. So when you mention same rate as for random shuffling, what exact rate do you refer to from which work?
So this is just the standard, in this case, just the standard SGD rate of sigma squared, square root of sigma squared over total number of iterations. Okay, so you don't mean actually shuffling, but you mean with replacement, not without replacement. Not that you shuffle and you go through this. Here, okay, so I'm assuming here that this is for one pass SGD. So I'm assuming here that each one of these documents is a random draw from the distribution. Yeah. And when I say with random shuffling, you can think of it this way. If I was to run for a million iterations, then I would draw a million times from the distribution. Or if I got a million draws from the distribution that were not, that had some structure, I'd then shuffle them internally. Okay. So the shuffling here, I'm sorry for the confusion. When they say random shuffling, random shuffling is also used in thinking about sampling with replacement or without replacement. This is not the same type of shuffling I'm referring to. There's no replacement here. Everything is IID from the distribution. The question is just, is it IID, all IID from the average distribution, or is it draw an IID from the purple, then IID from the green, then IID from the purple, then IID from the green? Does that, Peter, does that answer? Yeah, totally. Thanks. Sorry for the confusion with that. Yeah. Okay, excellent. Okay, so what we saw here is an example of how by using pluralism, by using this idea that we do not need to insist on the same model for all the machines, we're fine with having different models for different machines, we could completely alleviate the issues of heterogeneity relating to the semi-cyclic structure or the diurnal variations. And the challenge I'd like to end this talk with is that I believe that the same type of idea of using pluralism can also help alleviate other challenges with heterogeneity having to do with differing number of samples per machine or differing delays or processing times in each machine. This is still things that need to be figured out. Okay, I think I'll end here. And if there are any additional questions, I'll be very happy to take them.
Okay, thanks a lot. Very good. So the floor is open to questions. Feel free to raise your hand virtually or type your question to the chat box. And while we're waiting for these questions, could you maybe hint at how you would look at these other types of heterogeneity and pluralism? Or is this ongoing where you don't want to reveal?
I know, I'm happy to, it's not, I wish I could say I know the answers, but I want to keep them secret, but I actually don't know how to do this. I mean, we have some ideas, but I think it's too vague now to really know. So I think that for the amount of data, differing amounts of data per device, that I have a bit more sense of how to do this, and the fact what you can do here, and this is related, I think, also to some of the work that maybe you did with Philippe Hensley. If you think about maintaining a different iterate per machine and introducing a term that tries to tie them together, but allowing each machine to have different, the iterate per machine to be different, and updating those iterates, you get updates that look very similar to standard kind of gradient updates in the entire system, but with different weights, and those different weights can allow you to account for the different number of samples per machine, and things can kind of deviate from the consensus differently, deviate from the average differently. I think this is fairly vague answer, but this is in part because I think we still don't know exactly how to do this. But I think ideas along those lines can be helpful here. For the differing delays, I think this is a very big problem, very challenging problem. And this is really where I don't exactly know how to do this. I mean, this is a real problem because right now, I think what happens in many systems is that there's some cutoff time that machines that don't get back to the server after a certain amount of time just get cut off. And this is a very sensible thing to do if you have the same data distributions in each machine. I mean, you should just say, just forget about the stragglers. I mean, I have enough data. It's not worth my while waiting for the stragglers. But with differing distributions in different machines, again, cutting off those stragglers is might be cutting off a huge chunk of your distribution. But waiting for these stragglers slows things considerably. And here, I'm not entirely sure how to address this, but again, some idea of having a model for the stragglers, different models for machines of different sort of delays or different speed, and where those different models are related among themselves elastically somehow, so the slow machines can also get the benefit of the fast processing that happens in the fast machines without their unique characteristic getting starved out. I mean, this is now very vague, and I do not know, I mean, how to do this.
Yeah, there's a clarification question by Saida. I unmuted you. You can ask the question yourself.
Hello, everyone.
Yeah.
Thank you so much for your very nice presentation. I just want to ask you to give me more explanation about that averaging, because it's not very clear for me how it can help. At the end, for me, it's like even if I have different blocks, at the end, it's the average over blocks, right?
So what you're averaging only within each block. So you're running a single SGD chain, and then at the end, after you finish running your SGD chains, you get a different model for each block. So in this case, in this example, there are only two blocks, block 1 and block 2. And so the purple is 1 and green is 2. And at the end, instead of outputting a single predictor W, you actually output two different predictors, one on purple data, on data sampled from the purple distribution, and that's going to be W tilde 1, and a separate one for use on the green distribution, that's going to be W tilde 2. And W tilde 1 is obtained by averaging the iterates encountered during the last purple block. And W tilde 2 is obtained by averaging the iterates encountered using the last green block.
So basically, you classify the users based on their similarity somehow, and then average over that specific.
No, what I do here is I don't classify the user based on similarity, but just based on when they're active, or rather based on when they participate in the process. So to actually use this in devices, you check for which device, what times is it typically available, and to devices that are typically available during the purple times, you'd use model W tilde 1, and to devices that are typically available during the green times, you'd use model W tilde 2.
If it's possible, for example, to cluster the users and then get the average over those, and then, I mean, define the block based on the similarity between users, or what do you think about that? Because I was thinking that it can somehow handle the heterogeneity between users.
Right.
I don't know how to explain it, but I think the blocking idea is very great.
Right.
And it can be applied in different scenarios.
Right. So I think that in this example, we were actually happy that we did not need to explicitly cluster the users or discuss in any way how the users are similar or not similar to each other. So the solution here, the pluralism, the solution directly relates to the type of heterogeneity we encounter. The pluralism is based on the time of day of availability, which is exactly the heterogeneity we have here. We do not need to do any type of clustering for the users. If I do clustering for the users, then I have to really start talking about, how are what do I mean by similar? How are things similar and not similar? And here I was very happy to not have to even define what it means to be similar or not similar. You're right that in other cases, it definitely could be, in multitask approaches, for example, it definitely could be useful to have some kind of clustering of users based on some notion of similarity.
Okay, thank you so much. Thank you.
And I see there's another question here. Okay, so right, so the question here is how many blocks am I allowed here? And so the answer, let me just read the question. How large could you allow the number of models be? Right. This is, I think, what Kongma is asking. How large can B be to keep its performance the same as usual S3D with a single model? So there are two questions here. So from a statistical perspective, B doesn't matter. I mean, no matter how large B is, I still get the same performance on average. So the expected performance would be the same. The difference would only be in the concentration term, and B can be still very, very large. You'd still get decent concentration. So that's less of an issue. And again, the problem is not an expected generalization error. It's just in how well it concentrates. The bigger issue here is with engineering overhead. So when B is very, very large, we start needing to have lots of models and distributing lots of different models to different devices, and that might get. And so if you want a number, I would say that if you take B, if you're talking about the urinal variations, and you take B to be something like 12 or 24, then that probably captures the urinal variations very well. We don't think granularity of 1 hour is usually more than sufficient for that, and handling order of 12 to 24 models is still reasonable engineering-wise in terms of dealing with that number of models. But really, I think the issue here is not so much balancing. The theory works with any B. I mean, the issue is balancing B with engineering challenges of actually implementing this. Does that, Kongma, does that answer your question?
Yeah, thank you.
Okay.
Thank you.
Yeah.
Any more questions, anyone? So there's one by Mehdat. Let's give him voice.
I think that's not a question.
There's another question.
Actually,
okay. I actually didn't read it. Okay.
there is time. I said it's over, but if there's time,
maybe you have a question. If you have a question, you can ask Mehdat.
Okay. Yes. Yeah. Sure. Nati, I like the idea of adding this personalization to learning, but can you a little bit elaborate on this? How do you see that as because global model is not good, as you said, if heterogeneity is high.
So we have several papers in that I skipped very quickly. I mean, I didn't really describe it. I think I just put maybe I put the references to them, where we showed how to do that. The thing is that then it really depends. In order to do that, let me go pick those references again. In order to do that, you really have to define the notion of similarity. Like, what does it mean that two models are, the different distributions are similar but not identical? And I mean, this is something that the multitask community or transfer learning community has been dealing with for a long time now. And we looked at, I should say, many of these papers are very simple. And so we looked at that for different notions of similarity, how you can do that, how you can do this distributed optimization where the goal is to output different models for each machine. And I should say that for this, there are also others. This last option, which is just looking at the Euclidean distance between different models, is maybe the simplest. We looked at it in a graph-based approach. There's also work by others that look at distributed optimization for this multitask setting. I think Virginia's and co-authors have a paper about this, and this is essentially what's happening. And also a paper that Philippe Hensley mentioned recently together with Peter. I mean, they don't talk about it as distributed, as they don't explicitly talk about it as multitask learning, but that's essentially what's going on there. And so we do have methodology for doing this, but again, it depends on the notion. You have to define some notion of what does it mean for different devices to be similar but not identical.
Okay, thank you.